Hi everyone, thank you for coming to this talk. My name is Sebastian. I'm a technology programmer at Techland. I've been there for 4+ years at this point. And today I wanted to share with you how we integrated our terrain and CityBuilder systems. Jakby jeszcze działało, to by było super. The agenda for this talk is, for this presentation is as follows. First of all, for those of you who didn't see the Digital Dragons presentation on CityBuilder, I'll briefly explain to you what it is. Jest git. I'll show you some of the most common problems of using CityBuilder and terrain together. I'll go over our previous approaches to fixing these problems. Then I'll move to the final approach. And in the end, I'll give you an overview of how all of that is actually integrated as a whole system. So, CityBuilder. This is our graph-based tool for procedural content generation. What you see on both of these screenshots is the exact same place, both in-game and in CityBuilder graph. As a user, you draw these 2D shapes, choose appropriate settings for them, and press generate. When you're almost happy with the generation output, but you want to tweak some things, you can always lock this content to modify it by hand. Now, as for the graph itself, the most common element types are these nodes here. They are singular points, and even though graph itself is 2D, they create these 3D helpers so that they can be moved around in any axis. And also, when conditions are met, these nodes will create crossroads. Nodes can be connected with each other to create edges, and edges can be parameterized to create roads. Now, when we draw the last edge, a polygon forms, and these polygons are called areas, and for the most part, they generate either buildings or nature biomes. As mentioned before, edges can generate roads, and when conditions are met, nodes generate crossroads. These conditions are, for example, the number of edges for a node, or the angles between these edges. Now, the roads are built using these small slices of the road, which are called profile meshes. They are then extended along the edge and tessellated properly in case of curved edges. They are also used quite extensively by the final solution that I'm going to discuss later. Alternative way of building roads is by arranging these pre-built road modules, like the one selected here. Initially, this system was used strictly for road decorations, like lampposts or benches, but in the end, it turned out to be quite useful due to how easy it is to add unique road segments. So, because roads and terrain are separate systems, it is inevitable that there's going to be some visual issues. Now, the most common one is when roads don't match the terrain below them and they float above it, and this issue is even worse when the terrain below is removed, since then you can see the void. More subtle issue was when sidewalks are much higher than the road itself, because then when you try to match the terrain with the sidewalks, you might overshoot it. Then you have to correct it in the middle, and you can imagine how tedious it gets after a while. Additionally, our areas can generate ground planes or ground meshes. These are there in case areas want some special texturing for them. And this also means that we essentially have two terrains on top of each other, and not only does it produce unnecessary geometry, but it also can lead to some mesh clipping. So, at this point, we knew that we wanted to have the freedom of moving these roads around and not have to resculpt the terrain after each edit. And at that time, we already had one solution for this. Roads in Dynac 1 use this system that would generate these filler meshes to the sides of the road. They would connect the road with the terrain, and with some shader magic, it will be blended pretty nicely. Unfortunately, magic or not, this was sometimes obvious that these were additional meshes, either because of texture mapping or because of lighting. On top of that, this is just a partial solution. That is because this only addresses the issue of holes under the roads, but doesn't help us in case the terrain is higher than the road. And since it's a pre-CityBuilder solution, there's no support for areas. On the plus side, the generation of these meshes was really fast. So we knew that we wanted to work with terrain directly to support the cases where the terrain is higher than the road and support areas. And here came the idea of meshes modifying the terrain. The idea was simple enough. For each terrain vertex, we would search around for close by CityBuilder meshes, find suitable points on them, sample their height, the distance to these points, and calculate the slope based on that. Now we could approach this in one of these two ways. We could either find the closest point on mesh geometry, which would produce us high quality results, but the con of this is that this is quite tricky in case of some complex meshes. And it's also quite expensive if you consider that we have to do it for each terrain vertex for each mesh around them. Now, alternative for this is to rasterize these meshes into flat textures so that we can, for each terrain vertex, we can search around for the closest rasterized pixel and use it as a sample point. This is much simpler to implement, and these textures can be cached since we only have to re-rasterize these meshes only once a CityBuilder element gets modified. Now the con is obviously the quality is highly dependent on the resolution of these textures. In the end, we went with the rasterization route simply because it was much easier to implement. This is what it looks like whenever we rasterize a mesh into a terrain height map. All of these pixels to the left are the same color because both ends of the road are at the same height and this road is flat. And to the right you see a height map when all of the other pixels are searching around for the closest raster pixel and are fading based on the distance. And this alone looks quite promising, but this is unfortunately a very simple case. Now when we move to a bit more complicated one, where one of the road ends is at a different height, which is represented by this fading color, we see that the slope at the right side tries to follow this fade, but unfortunately, when we zoom in, we see an issue. That is because for these, in this case, for these three highlighted pixels, we see that the colors are going from dark to lighter to dark again. Now, if we consider this to be a height map, then these values are going to produce us a terrain spike. Or more precisely, it's either going to be a terrain spike or terrain drop. Now, what's even worse is that this terrain drop is going to occur right at the edge of the road. And so not only does it look bad, but it also fails to help us with the issue of holes under the road. But why does it actually happen? And that's because of the way we search for the closest points. When we loop left to right, top to bottom, these are going to be the first closest points that we find. And even though highlighted pixels are right next to each other, their sample points are quite spread out, and this is a sole reason for these value jumps. Now we could try to fix this by either increasing the resolution, by changing the way we look for these closest points, or by looking for more than one closest point, but unfortunately neither of these helped us a lot because we actually tried them, and yeah. So after that, we decided that we want to pursue a similar algorithm, but instead of this numerical approach, we wanted something to be more analytical. And we either could try to search for these closest points on mesh geometry, but instead we went and used our CityBuilder graph. Now, the idea is similar, only this time instead of searching for nearby meshes, we would search for nearby city elements, and sampling the closest point would have to be different for each CityBuilder element type. Now, the only question is if the graph can provide us enough data And for areas, it's actually pretty straightforward, since these are just polygons with 3D vertices. We have everything that we need. For edges, we have what's the most important, which is the line segment and road width. But unfortunately, with that, we can only assume that these roads are going to be flat and symmetrical, which is not the case. And for nodes, we only have their starting position, which is a problem, because crossroads can be any mesh with any shape. So we don't have any information other than the mesh itself, which we do not want to use here. So what can we do about this missing data? For once, we can just focus on what we have and forget about the problems, right? So to the left side here, we see a picture that is very similar to before, only this time, instead of rasterizing a road, what we do is for each heightmap pixel, we calculate the distance to the edge, and if that distance is lower than the road width, and then it's set to the road height. But the right side picture looks a lot different now, and that is because this raster shape from before is gone. The pixels that are almost inside the road get a very low distance to the road, and their height is calculated to be almost exactly the road height. And since we are no longer looking for these closest pixels, we no longer have this issue of value jumps. Now here's a comparison of these two approaches, and as you can see, this right slope is a lot more consistent and smoother. This is what it looks like in real-time in editor, or at least it should be real-time, because it's kind of janky here. Since we are only using a line segment and road width, we don't even need this road mesh there. Now for areas, we need a more sophisticated algorithm, and we needed to be able to sample a point inside a polygon and blend the values of each vertex. Where for us the vertices would be the nodes, and the values that we wanted to blend would be their heights. After a bit of trial and error, we settled on this research paper titled Blended Barycentric Coordinates. How that works is for each sample point, we calculate a weighted average for the nodes, where the weight of the node is given by this formula there. You can think of it as a sum of the weights of the edges, of the nearby edges, divided by the distance to the sample point, where the weight of the edge is dependent on the angle. That is because edges that are closer to the sample point create a wider angle, and that is the same for longer edges. They also get a higher angle, and with that they get a higher weight. We even got this to work with concave polygons. For this, for each sample point, we would trace each node and create this visibility polygon, and use this polygon instead of the original one for calculating the gradient. This is what it looks like in editor. It's a pretty smooth slope. We even get this saddle shape here, and it's much faster than what we expected initially. Okay, now we have to go back to the missing data we just ignored before and actually take care of it. So far we've assumed that roads can be described just by their start end points and their width, but this is unfortunately not the case for this road right here. And not only is it completely one-sided, but it's also completely not flat because of this shape going down. For this, we used our profile meshes. Since they are just slices of the road that get extended along the edge, we can treat them as sets of 2D segments. And with that, we can just search for the most extreme points to both sides and get two separate horizontal offsets and two separate vertical offsets, where the vertical offsets are crucial for calculating the correct slope height. Now here we have only one point, since there's only one side of the road, but so we could say that the width and vertical offset of that second point is 0. But these points didn't help us in this case. Here we had to implement terrain alignment inside of the road itself. For this, for each terrain vertex that would fall inside the road, we would once again use the profile mesh, but this time we calculate the distance to the edge, and using that distance, trace a simple ray vertical ray into these 2D segments to calculate the exact height of the road at that point. And with this height, we can align this terrain properly over there. Now for Crossroads, we unfortunately didn't have any tricks that could save us, and we had to introduce a requirement. And this requirement is that if a crossroad type would be to align the terrain, it would need this, this polygon describing its shape. And with a polygon like this, we could find the closest point pretty easily and calculate the distance. Fortunately for us, crossroads are, even though they can be any shape, they are most likely to be flat. And for the few cases that were not flat, they were just aligned by hand. Now, for the slopes, a simple linear fall-off would be boring, so we used our curve editor for that. We can build our library of curves, and then for each element, we can select which curve it wants to use for the slope. Cool. Nodes in these curves can also define material overrides. And they get then painted automatically on the terrain. And this is especially useful if you want to create paths on terrain like dirt roads. Additionally, we made it possible for each element type to remove terrain triangles that it covers completely. And this is useful for not only reducing the geometry count, but it also helps us with the issue of ground meshes created by areas and the possible clipping of meshes. Now let's take a step back and look at it as a whole system. Whenever a city element gets created or modified, we run its dedicated algorithm for the element type. And then a result of that algorithm gets stored in a texture like this. This is essentially a slice of a height terrain height map that is going to be then projected onto the terrain to blend it with it. Each pixel in this texture stores the height of the sample point that it found and the influence it wants to have on the terrain, where this influence is calculated based on the distance and the slope that was assigned to this element. Now, since these elements can be processed independently and we wanted this to be non-blocking, it just seemed natural to move these to the background thread. So now whenever each element gets modified, it queues a job, and then this job gets consumed by one of the 4 threads in the background. Whenever a job finishes or terrain gets modified by hand, we run composition. Our terrain works with a stack of layers, where the initial layer will set the initial height map that was provided by the user, which is the height map that you modify by using brushes. But then after that, we run other layers that work like post processes, and the one we are interested in is the CityBuilder layer. What it does is for each terrain chunk, it'll search around for the nearby CityBuilder elements, get their cached textures, blend them into the terrain, mark triangles for removal, and set the material overrides. With a layered approach like this, what it gives us is that we don't have to worry about losing the initial information. We can just move these roads anywhere at any time without overriding the initial height map. Now here's a funny slide, and this is a summary. I told you it's funny. So here's a summary. If you have any questions, don't hesitate to ask.